You might not expect this, but there's a system that can stop dangerous objects before they even reach our atmosphere. Arrow-3 operates so high above Earth that its interceptions actually happen in space. Today, you're going to see how this surprising technology works and why it has become one of the most talked about systems in the world. Hello everyone, welcome back to the channel. Today we're exploring a system many people only hear about in headlines but rarely understand. Arrow-3 is designed to intercept incoming threats far above the Earth, long before they drop into the atmosphere. This unique approach gives countries more time to react, analyze, and prevent large-scale damage. The core idea is simple: stop the object early so nothing reaches sensitive areas below. To do this, Arrow-3 uses long-range sensors, early warning networks, and a guided interceptor built for high-altitude performance. Unlike traditional systems that work within the atmosphere, Arrow-3 operates in exo-atmospheric space where air resistance is nearly zero. That means its guidance, speed, and precision rely heavily on advanced computers and tracking algorithms. In this section, we'll lay the foundation for how the entire system fits together. You'll see how detection, communication, and response form one continuous chain. As we move deeper into the script, each part will reveal another layer of how space interception actually works in the real world and why it has become such an important capability today. Arrow-3 begins with very early detection, and that's where its network of radars and sensors becomes essential. The moment something is launched, distant tracking systems try to identify the type of object, its path, and its possible target. These sensors look far beyond traditional ranges, picking up data from many kilometers away. What makes this system different is the precision of that early information. Instead of waiting for the object to get close, the network instantly sends the data to command centers where powerful computers simulate the incoming path. This helps determine whether an interception is needed. If the object is considered dangerous, the system begins preparing the interceptor. Because everything in space moves so fast, timing is absolutely critical. The earlier the system reacts, the more accurate the interception becomes. In this section, we focus on how data collection forms the first building block of Arrow-3's success. Without immediate and accurate detection, the interceptor would have far less time to adjust its path. The entire system relies on this early decision making, which makes it a major advantage compared to older defensive technologies. After detection, the command process begins. This step is all about understanding the threat, analyzing the data, and deciding whether the interceptor should launch. Teams monitor detailed simulations that show potential trajectories. These simulations update in real time as more information arrives. The system doesn't rely on a single reading. It combines multiple streams of data to create a full picture. Once operators confirm that an interception is necessary, the launch command is prepared. This is where the precision of Arrow-3 becomes clear. The interceptor doesn't simply fly toward the target. It calculates a predicted meeting point far outside the atmosphere. Because the target moves extremely fast, command teams need to adjust calculations constantly. The goal is to place the interceptor in the exact location at the exact moment the target arrives. This requires coordination between computers, operators, and communication networks. The command stage ensures everything is synchronized. In this section, we see how human decision-making and automated systems work together to achieve a reliable result. Without this balance, space interception wouldn't be possible. Now we reach one of the most impressive parts, the interceptor itself. Arrow-3 is built to operate in conditions where there is no air pressure and almost no resistance. That means its engines, control surfaces, and sensors are all designed for space-like environments. Instead of using traditional fins or aerodynamic control, It relies on small thrusters that adjust its direction with remarkable precision. These micro adjustments help the interceptor stay aligned with the target's predicted path. Its onboard computer constantly receives updates from ground systems, allowing it to correct its trajectory while traveling at extremely high speeds. The interceptor also carries a specialized kill vehicle designed to eliminate the target without relying on explosive force. Instead, it uses speed and accuracy to neutralize the object cleanly. This reduces debris and improves overall safety. In this section, the focus is on the physical design of Arrow-3. Every component is built with one goal in mind: reach the target quickly, stay stable in high-altitude conditions, and perform with absolute precision. During flight, the interceptor enters a phase where it must adjust its path based on both predicted movement and real-time updates. Because the target may change direction, the interceptor needs to stay flexible. That's where mid-course guidance becomes essential. Using commands from ground stations and onboard sensors, Arrow-3 refines its path every second. Its computers create a moving 3D map of both objects and compare the predicted collision point with live data. If anything shifts, the interceptor shifts with it. This level of responsiveness is what makes space interception effective. Even small changes in timing or direction can determine success or failure. Another important aspect is energy management. The interceptor must use its propulsion efficiently because space maneuvers consume a lot of fuel. Each adjustment is calculated carefully to keep the interceptor within range. This section highlights the intelligence guiding the flight. The interceptor isn't just fast, it's aware, adaptable, and constantly analyzing the environment. That combination is the key to reaching the target with high accuracy. When the interceptor gets close to the target, the final approach begins. This stage is where precision matters the most. The onboard sensors activate fully, tracking the object independently while ground systems continue sending updates. In space, objects move at incredible speeds, so timing must be nearly perfect. The interceptor aims for a direct hit, using calculated force rather than explosives. This is known as a hit-to-kill approach. The purpose is to neutralize the target cleanly, reducing the chance of fragments falling toward Earth. The final moments involve the interceptor making rapid micro adjustments to match the target's exact position. Even a tiny shift can determine whether the interception succeeds. This phase demonstrates the advanced engineering behind Arrow-3. The system's ability to guide itself with such accuracy separates it from older technologies. In this section, we see how technology, timing, and guidance algorithms combine to create a highly reliable interception. Once the interception is complete, ground systems immediately begin analyzing the event. Engineers look at data from sensors, communication logs, and trajectory recordings. This information helps determine if the interception was successful and what improvements can be made in the future. Even when the mission goes as planned, every flight teaches something new. This is because space interception involves physics that respond differently depending on altitude, speed, and object type. Post-event analysis also helps refine future simulations. The more data the system collects, the smarter it becomes. This constant learning cycle strengthens overall reliability. In this section, the focus is on what happens after the mission ends. The process doesn't stop with the interception. Instead, data from each event strengthens the next response. This is how long-range defensive programs continue to improve year after year. Arrow-3 is not a single unit. It works as part of a larger ecosystem of early warning systems, detection networks, communication lines, and command centers. This broader network ensures that multiple layers of protection are available. Each layer has its own purpose and range. Arrow-3 fits into the high-altitude tier, working where atmospheric systems cannot. The cooperation between layers creates flexibility. If one system can't reach a target, another system can. This layered approach increases the chance of identifying, tracking, and neutralizing threats early. In this section, we look at how Arrow-3 interacts with these layers. It doesn't operate alone. Every detection sensor, radar network, and communication channel contributes to the mission. This teamwork helps maintain performance even in fast-changing situations. The development of Arrow-3 required years of research, engineering, and precision testing. Designers had to solve challenges related to speed, altitude, and environmental conditions. Creating a system that operates beyond the atmosphere means rethinking traditional defensive technology from the ground up. Engineers tested materials that could handle extreme temperatures, control thrusters capable of sharp movements, and guidance computers that could run complex calculations instantly. Simulations played a big role in shaping the interceptor's final design. Every improvement from propulsion to sensors came from repeated experimentation. This section focuses on the effort behind the technology. Achieving reliable space interception takes time, creativity, and thousands of tests. The result is a system designed to perform under some of the toughest conditions possible. Arrow-3 represents a major step forward in long-range protection technology. Its ability to intercept threats outside the atmosphere provides extra time, extra safety, and extra precision. Throughout this script, we explored how detection, command decisions, guidance, and final interception work together. Each part is important, and each part adds reliability. This system shows how advanced engineering and smart design can reshape protective capabilities. As new technologies continue to grow, systems like Arrow-3 will play an even bigger role in global safety strategies. Understanding how these interceptors work helps us appreciate the complexity behind them. In this final section, we wrap up the story of Arrow-3 and the space interception method it uses. It's a technology built for the future, designed to stay effective in rapidly changing environments. If you enjoyed this breakdown and want more simple, clear explanations of advanced technology, make sure to like the video, subscribe to the channel, and share your thoughts in the comments. Your support helps us bring more content just like this.